mostly people who are working in the same field have the same perspective, mostly. Okay? The most variety you can get is from personal questions. Something like, can you tell us about your life in Germany, perhaps? But then that isn't the
same. We try to ask questions either based on what they have already answered, or if we can find a personalized question that they will be excited to answer, we ask them that. That's the only deviation. Otherwise, everything is standard because this is a.
Yeah, sure. So shall I speak to the camera?
Anyway.
So I'm Tom. I'm a theoretical physicist and I'm a PhD student from Munich, so Technical University of Munich in Germany. I started like a year ago when I work on heavy ion collisions from the theory side, basically.
Welcome to the Phi I documenting series, the Quarkonium workshop. Yeah. So my name is Aditya Dwivedi, and we have got Dr. Tom, or
not yet Doctor.
Not yet Doctor. Yeah. In the Quarkonium workshop. So what is the workshop about? Would you please brief us?
If you can explain it in a way that undergraduates would, capture.
Because all of us here are like second year.
Yeah. So I mean, the workshop does have quite different topics, to be honest, like different tracks. There are always different sessions, but mainly the broad topic is, so you know what Quarkonium is? Quarkonium is basically a bound state of two quarks, like a quark and an antiquark. That's Quarkonium. And basically, you can describe, especially heavy quarkonium is what we are talking about, and we are exploring basically the properties of these particles, like how often they are created in collider experiments, and their behavior. For example, iridium is what I study, but also other exotic particles, which could, for example, consist of more quarks than just two, and recent experimental and theoretical results for these type of particles.
Can I ask a question?
Yeah, sure.
Yeah.
What's the difference between heavy quarkonium and not heavy quarkonium?
Well, so in the standard model of particle physics, it consists of, like, it has different quarks, right? You have the up quark, down quark, then you have strange, charm, bottom and top. And you usually say that, for example, charm and bottom are heavy quarks because they're just heavier, literally in the sense. And the other quarks, for example, up, down, and strange are lighter, and the tools to treat them and their behavior, so also the theoretical calculations, are rather different for these light quarks, and so that's why heavy quarks is a different topic. And then the top quark, for example, doesn't form bound states because it's too heavy to actually do that. It decays, like it can't form bound states essentially. Yeah.
In the ask another question. So as a PhD student, you're like let's say closer to where we are than the professors here, there here, right? Yeah. So as a PhD student, how would you say, like, why did you take this field? I mean, how would you answer the question if someone asked that? I mean, like, what's the reasoning behind it, and why is it exciting for you?
Why I take the particular field or the scientific?
No, particular field.
Particular field. Okay.
Basically, we are physicists.
Okay.
Yeah,
so, I mean, for me, I always was interested in theoretical physics, for sure. I was just, when I had, so in my university we had different classes for theory and experiment, and I just realized for me the theory classes were the ones I liked more. I always wanted to exactly know how things work and dig down into derivations and calculations. That's just what I like more. So I knew I wanted to pursue theory, and then it's the question if you do condensed matter or particle physics, right? And in my case, it was just that particle physics was more intriguing to me. It's also maybe a little bit, to be honest, at my old university, particle physics had maybe a little bit, we had more faculty members in particle physics, right? And then you also pushed a little bit more to it, but in general, I don't know, I just liked it more, and I really like to explore, like to really understand the fundamental things, and that's fundamental physics, like, for example, particle physics.
So I have a question.
Yeah.
Can you share one instance when your research collided with something truly unexpected or counterintuitive, like that keeps you really charged to the field and your research?
Something.
Yeah.
Some
phenomena.
Research problem you are working on for your PhD.
So right now, what I'm working on is the suppression of quarkonium. So really, I look at bottomonium, so quarkonium made of a bottom and anti-bottom quark, this bound state. And what happens is in heavy ion collisions, so when you collide nuclei of, for example, lead, two heavy nuclei are collided at, for example, CERN, and what happens is they are produced, and there's also something produced called the quark-gluon plasma, and that's like a hot soup of light quarks, of up and down quarks, for example. And they are in a certain state of matter. They are not a bound state, right? You know that usually you don't have free quarks, right? You don't have like a single quark flying around here. But there, in this case, you have this hot soup where they are not confined into bound states, but rather into like a weird state of matter. And now this heavy quarkonium is traveling through this hot soup, and they interact with each other, and I basically look at that. And the motivation for that is that this quark-gluon plasma is interesting because it's a weird state of matter, and something similar must have been created in the early stages of the universe, because it was also very dense and very hot at the early stages. And so it's interesting to study this state of matter, because it's interesting also for studies of, for example, dark matter in the early universe. And so this idea that the botamonium was traveling, because initially you don't know if this quark-gluon plasma is created in the experiment, right? You can't see it, you can't watch it, you have no idea. And so you must find a way to prove that it exists. And one of the ways is looking at this botamonium that's traveling through the quark-gluon plasma. And what happens is it dissolves in this plasma. Like, for example, a sugar cube dissolves in coffee, right? If you put it into something very hot, it dissolves. And now the idea is, at CERN they also do proton-proton collisions, right? And there you also produce these botamonium particles. But you do not produce a quark-gluon plasma, because proton-proton is just essentially 6 quarks colliding, right? So you have a very low density and you don't have the temperature. But at heavy ion collisions you have a lot of, right? I mean, it's a lead, like you have a lot of protons colliding. And then this quark-gluon plasma is created. And so the idea is, in proton-proton collisions, the botamonium will not dissolve in this hot soup, because the hot soup is not there. On the other hand, on the heavy ion collisions, it will dissolve. And so what people do is, they measure in proton-proton collisions how many of these botamonium particles do we see. Then they measure it in heavy ion collisions, and they measure less in heavy ion collisions, because they dissolve. And then they can say, the reason for this, that we measure less, is the quark-gluon plasma. And that's how you can, for example, prove that the quark-gluon plasma exists. And we study this basically, we make predictions. So I work in theory, we have a model, how to describe this quark-gluon plasma, how to describe the botamonium, how to calculate really observables and compare it to the experiment.
Can you share any challenges you faced while doing research in high energy physics?
Yeah, I mean, for me it's really, people are different, right? And I'm very good, I think, with numerics, programming, all this type of stuff. What for me is hard is really the very tough parts of quantum field theory. That's what I found most challenging, and still find so. I mean, the theoretical tools are quite sophisticated, so.
Could you describe the future of maybe high energy physics in a few words? Any interesting development that we can focus on?
I mean, that's tough. I mean, high energy physics is a broad topic, right? I mean, in general, of course, you have these very big questions of dark matter and so on and so forth. I mean, one has to say that in 2012 the Higgs boson was discovered, right? And people knew that it would be discovered. It was really an integral part of the standard model by then and our theoretical understanding. After that, I would say we did not have like a major discovery or breakthrough. But of course, we are very sure that the standard model, the way it is not complete. And so people are searching for it. We don't know, and people are coming because nowadays many properties of the standard model have been measured and verified quite precisely. Some have not. For example, what we are dealing with here is QCD, right? The strong force that holds things together. Calculating stuff with that is very hard. So sometimes you can't even make accurate standard model prediction with that, right? So, but in general, a lot of stuff has been verified, and it seems to agree, so we don't know where, for example, new physics lies, something like that. But first of all, I think there are two things in the terms of QCD. What we are doing, improve the tools that we have to even compute things, to understand it, which is interesting and which is really hard and challenging. And of course, we are making step-by-step progress towards that. And then searching for new physics, which does not fit in the standard model. It's a big topic in, of course, high energy physics, and we don't know how to do it. I mean, there are different strategies for searching for it, but haven't found anything yet, and maybe we have to come up with new strategies and elaborate our searches. I mean, we will see. But I mean, I just want to say, sorry, because some people say, high energy physics is like in an era where it's not interesting anymore, because the interesting developments have been done in the last, I don't know,
80s,
years.
90s?
Yeah, I mean, and Higgs boson and stuff has been discovered, and now for 10 years nothing has happened. Some people are saying that, but I don't feel like that, to be honest, because research, I mean, in many cases, it's not like you always go upwards, right? You always have a plateau where things need, and then you just need to break out by developing new methods. So right now is the time to develop new things, to try new things, and something of it will work, and something will lead to interesting new things. So yeah.
That's what I was going to ask actually. Is experimental limitations not driving new physics, or are there theoretical advancements already but we don't have the sophisticated experimental tools?
Well, yeah, I mean, of course, there are a lot of theories that one could test better with a much larger experiment, but of course things are limited. Like, I mean, if you look at so there are proposals, for example, future colliders to be built, right, larger than CERN, and if you look at, I mean, you have to justify it to people, because in the end someone has to give you money, and so clearly it would be nice to have like a huge collider, something new, maybe even like people are talking about a muon collider, because you can, like, it has advantages over other colliders, but in the end it's about getting the money. But there are experiments on the way, and for example the electron-ion collider, which allows especially to study some of the things discussed in this workshop, right, related to the strong force. There are other experiments in terms of high energy, and maybe we will one day get a lot bigger collider. But of course, getting a bigger collider does not guarantee you to
Yeah, exactly.
I mean, you don't know, right? And so that's also why it's hard to pitch it to people, right? Because saying, yeah, we will for sure find dark matter is just wrong, right? And so then telling someone, okay, can you give me a lot of money, so maybe something will come up, it's also not easy. I mean, it's not that way, right? I mean, you can also guarantee some things that you can do with a new collider, but this holy grail of, for example, new physics, you can't ever guarantee of finding at the moment. Yeah.
I've got one curious question, last maybe, with the Quarkonium discovery that we prove in Large Hadron Collider, we can say quark-gluon plasma we can create it. In our like cold phase of universe, is there any such astrophysical observation or hypothetical scenario where we could make quark-gluon plasma, like could be possible?
Yeah, in the early stages of the universe. Yeah.
After that, could it be neutron star or something else?
So no, I mean, in the early stages of the universe, you have this type of quark-gluon plasma, because it's very space was things were very dense, very hot, and then you can have this type of, for a certain amount of time, right? But afterwards, the universe expanded, right? And then things cool down, and when things cool down, at some point the quark-gluon plasma will hadronize, one says, which means that the quarks inside the plasma will form bound particles, so for example Quarkonium, and so then you don't have it anymore, it dissolves. But still it's interesting, because what people try to describe is really what happened in these early stages of the universe, and for that you need some type of description then for example the quark-gluon.
Not in course of neutron stars.
I mean, neutron stars is a different story. It's also, of course, a compact object which is dense and so on and so forth. But yeah.
Lastly, how would you encourage any student to pursue physics?
Sorry?
A random student. How would you encourage him to go forward in physics and just pursue physics?
I mean, I don't know. It's you have to think about what is fun to you, right? And for me, I can say I always loved it to just sit in my room and study physics. I just enjoyed it, and I think that's the main cause. If that's the case for you, then you should pursue it. I mean, it's really, for me at least. I mean, I don't know. Everyone has different things that bring them joy, and for me, learning new things is just one of the things that is most rewarding to me, more rewarding than most other things. Yeah.
Building up on that question, that last question, like rather than just giving an advice for random physics or some random physics student, what advice would you like give to students pursuing physics who want to do research in any certain area? What is the general advice you want to give them based on how they must go over their courses? What kind of learning must they keep getting from it? What must they be thinking?
I mean, in principle, I would just say, of course, take the courses that are offered at your institution, right? I mean, you have certain courses that are offered in the direction you want to pursue. You have to take the courses, and then you have to find an advisor probably that does research that is most near to what you're interested in. And yeah, that's probably it. Yeah.
Thank you. Thanks a lot.
Yeah. Thank you.
Thank you so much.
Yeah, thanks.
Please introduce yourself.
Okay, my name is Tatyana. I'm from Russia. I live in Novosibirsk. It's like a new Siberia. So I work at Institute of Nuclear Physics, Budker Institute of Nuclear Physics. Here we have 2 ± colliders. I work on one of them and I analyze the data. It should be done with very high precision, and it's the main task. So it's a challenge to measure particle parameters in the wide range of energies from 2 to 11 GeV with a very high precision.
And can you give us, so we are all undergraduates, we are all physics, budding physicists, and we wanted to learn a bit more about the workshop. So can you explain the contents of the workshop to an undergraduate level?
Yeah, to us.
Okay, this workshop is devoted to very hot last published topics in particle physics. There are actually several topics from 2 sides, from experimental point of view and from theorists, and they discuss them together to better understand each other, to understand difference in experiment and predictions, and different predictions between each other, and different experiments also. So there are topics on there are topics on standard model, for example. It's mainly checks of precision tests on spectroscopy, where different masses are measured in the range by experiments. And there are some exotics. It's mostly searches and their explanations and predictions. And there was a day devoted to ion collisions. It's a specific range. So it's what I can remember.
How did you get motivated to do research in particle physics?
How did you find particle physics? Like, it's the thing that you want to do it.
Okay. Particle physics is the most fundamental part of physics at all. So it maybe sometimes it don't have a practical some practical things to do, but it helps us to understand what things are, from what they are made, what are the interactions, and many fundamental things, such as the standard model. I hope you saw this, and the extensions of standard model.
I heard that you mentioned the production of exotics. So can you elaborate a bit more on that? Is that something related to the, we hear the idea of exotic matter in popular science. So is that related to it?
Okay. In standard model, everything consists of leptons and quarks and bosons that connect them. Okay, so quarks, they have colors. So, 3 colors and 3 anticolors. So they can be gathered together in one thing, which has no color. It can be quark and antiquark, so they have color and anticolor. It's a meson called. And it can be baryon, where two quarks are gathered together, or antibaryon. Exotics is mostly when not 2 or 3 quarks gathered together, but there are at least 4. So it's exotics. It can be different things. It can be like molecular from 2 quarks, from 2 pairs, or it can be pentaquark when there are 5 quarks, which consist of. It can be various structure. Some of them said that 2 or 5 are not are weakly. Are not too strong connected with 3 others, and so there are different models how do they interact inside this state.
So are these like the bound states between these 4 or 5 quarks?
Yes, it should be bound state, because when it should be some bound energy near which it cannot this is not exist. This does not exist. But as there is a bound state, there should be some, as you know from quantum mechanics, it should be some near the bound, right? It should be some sensitivity to this answer.
Correct.
I want to ask a question. While experimental high energy physics undoubtedly hold immense intellectual stimulation, but it can also be a demanding field. How do you strike a balance between focus intensity required for research and broader pursuit of well-being? Even while studying physics as a student, we do play stuff. We do have hobbies of reading and
Basically, how is the lifestyle of an experimental physicist?
Well, I think it's everyday issue, right? To find this balance, especially when you are studying, because there are plenty of things, and much you study, it's much you can study.
Yeah, exactly.
So
how do you ground yourself? How do you not get overwhelmed by everything?
Immensity of knowledge.
You have to cut photo because there is a photo going on.
Okay.
Yeah, she is recorded.
Okay.
Thank you.
Thank you so much. So thank you so much for doing this. So can you explain the research which you are doing and the topic of the symposium to an undergraduate level, to physics enthusiasts like us?
This conference dedicated for physics problems of the Quarkonium. This is a particle which consists of quark and antiquark. The property of such a system is not well understood for us. Low range for low distance between the quark and antiquark. The situation more or less understandable for us. At the large distance, the interaction between quark and antiquark becomes so strong that we need special methods how to calculate the properties of such a system. It is a new, relatively new area of our field, because recently new experimental installations like a Large Hadron Collider and B factories provide many new and unusual results and qualitative effects, which is not completely clear at the moment. And this meeting, the experts in this kind of scientific field discussing the possible solutions, possible models for description of such objects. I think it is interesting for undergraduate students too, because the people who would like to continue with science could be considered this application or this area of research as a future track in physics.
And sir, can you tell us a little bit about your research particularly?
My research. I'm a member of Belle 2 collaboration.
Okay.
This E plus E minus collider with new universal detector which study the B quark, generally speaking. We are interested in the properties of B mesons, the mesons which consist of heavy B quark and light U or D quark.
Okay.
But also we are interested in highly excited BB bar states like epsilon or excited states of epsilon. And my personal activity concentrated on the study of properties, so highly excited BB bar states. And I had a presentation here with the recent results, and it was an interesting discussion about experts, among the experts. Okay.
Any questions?
Sir, how would you per se just how did you find your interest in particle physics or experimental high energy?
And especially in your specification.
In your specification.
I spent almost whole my life for this subject.
No, sir. How did you know that this was it? This is my.
How did you get interested in?
This was my thing.
To pursue just this.
When you were just about to enter the scene.
It is. I understood your question. When I was a student, the big quark was discovered just in 1977, and particularly in this year I graduated Universität, and the new object for research appeared, and I had a chance to study particularly this work because we have already the E plus E minus collider, which was able to produce such works. And my one of my first scientific research was measurement of the epsilon 1s invariant mass, just by the E plus E minus production of the epsilon meson. So then I continue with similar research, and it is quite natural. For me, it was natural to study particular this kind of physics.
I think that's it.
That's
Thank you so much.
Thank you for your time.
It's been a delight to talk to you. Thanks a lot.
I wish you success in your research.
Yes.
Okay. Thank you, sir.
Thank you so much.
Have a good day.
Well, strong interaction can be studied also with nuclear physics, but most of us, a lot of us are interested in particle physics. So the main subject of this workshop is on heavy quarkonium. That is a bound state of a heavy quark and an anti-quark. Well, I guess I should start with what quarks are.
I mean, we have a basic idea.
Okay, I'm talking to physics students, of course. So heavy quarks are the when we talk about heavy quarks, it is the usually we talk about the two second heaviest and third heaviest quarks, the charm quark and the bottom quark. Now the top quark is of course the most heaviest, but top quarks usually decay very fast into through weak interactions, so top quarks don't usually have time to form a bound state because they decay so fast. So heavy quarkonium, to form a heavy bound state, we need either a charm quark and an anti-charm quark, or a bottom quark and an anti-bottom quark. And of course, there's also the possibility to have a bottom quark and an anti-charm quark, and vice versa bound states. But the most common particles that we deal with are CC bar and BB bar bound states. So the most classic measurements that we can study are their masses, their decay rates. That's the area of spectroscopy. Also, their mixing. Mixing happens when two of those bound states are bounding energies are very close to each other, so that they can turn into each other by either emitting or absorbing light particles like a photon or a gluon. That's spectroscopy. There's also production. Production is, for example, the largest particle physics experiment going on is the LHC. LHC collides either a PP positron, proton-proton, or a proton or a heavy ion or heavy ion collisions. Those collision energies go extremely high. So current experiments are done at 13 to 14 tera electron volts, and compared to the mass of the proton, which is about 1 giga electron volt, that is quite a lot of energy. And from that collision, we can make all sorts of particles from the basic interactions of particle physics, and a very nice measurements can be made if we measure those heavy bound states, because they have very clear decay channels. So what we can try to do with that is to understand how strong interaction works with quantum chromodynamics by theorists computing those production rates and comparing with the experimental measurements. And there's also with heavy quarkonium, we can also try to see if we can probe the quark-gluon plasma, which happens when there are so many strong interacting particles together in a very hot state, which is believed to have existed in the early days after Big Bang. And also we may be able to probe that in other very hot and dense areas, like in other stars or neutron stars, things like that. So that is actually the subject that's going on today. What else? For recent years, there have been a lot of interest in other bound states that are not just a two-particle bound states. Those are, as a collective, they are called exotics. So they are what would be uncategorizable as simple two-particle bound states. So some candidates of those particles are either 4 quark bound states, 5 quark bound states, or some people call hybrids. Those are quark, anti-quark, and a gluon bound state. And of course, there are also all sorts of hypotheses about what those particles are. There are lots of measurements that have been done, and a lot more measurements will be done in the future. And a lot of theorists are trying to figure out what those exactly are. So there will be a brief overview of this conference.
Okay, I wanted to ask, what initially drew your attention in this field, like experimental high energy?
So I come from a completely theory background. So most of what I do is theoretical calculations based on how much I can use perturbation theory to calculate things, calculate what's measurable in experiments. So if we're lucky, some very nice observables are completely calculable in perturbation theory. In perturbation theory, we just split the interaction Hamiltonian and just expand in powers of that. But that's only possible if the interaction is actually weak. But we know that in QCD, low energy physics can have a very strong interaction between strong energy particles. So in a lot of cases, we do have to include those low energy, non-perturbative contributions. So it's very important for theorists to understand what those non-perturbative physics can do to the observable that you want to calculate, and how to account for that quantitatively as much as possible. So that's a very important area of research that is done theoretically. So most of my interest is in high energy interactions. So a classic example would be a energetic particle production in a collider, or it can be a decay of a heavy particle into light particles, so that all of the daughter particles will have energetic momentum, so that we can use perturbation theory as much as we can.
So, what do you think can a normal person be excited about in your field? Someone who's not from a very science background
at all.
I thought I was talking to physics students.
But the scope of our videos are meant to be for a wider public. So,
to science students mainly, I guess. But
yeah, but even for biology, someone who's about to choose their majors.
We actually have a program in which we choose our major after the second year. So until then, we study the basics across all 4 disciplines of science. I mean, broad disciplines: biology, chemistry, physics, and mathematics.
I see.
And we wish to, lure more physics majors.
So, what got me interested in studying physics is that we can. We are supposed to learn about the basic principles of those basic sciences in the introductory courses, and what's special about physics is that there are lots of problems that we can solve by directly applying those basic principles that we learned from those courses to real-world problems. I don't mean to badmouth other fields, but it is quite difficult to directly apply those basic principles to real-world problems. That is a hard thing to do. What is good about physics is that there are lots of problems that we can do with those basic knowledge. So, for example, what I do in research almost daily is start from those basic principles with the laws of nature, and start from that and reach at and in the end reach at calculating something that can be measured in an experiment. That way you have a clear view of the relation of what you do, what kind of measurement or observable you want to study at the end, and connect it all the way back to the basic principles of this science. That is very clearly done if you study physics.
I think that's about it.
I mean, any other questions?
Yeah, any other curious questions?
So I remember you mentioned something about exotics. Is that similar to the popular science idea we hear about exotic matter?
Well, the exotics that we talk about here usually decay very fast, so they don't survive long enough to produce matter actually.
Okay.
So the kind of exotic matter that we can do would be something like dark matter. So there are some candidate theories about dark matter that is similar to what we do in this workshop. That is a popular hypothesis that dark matter is made up of heavy particles that are loosely bound together. So that's one of the hypotheses that is studied by a lot of people.
Quarkonium is also heavy bound.
Yes.
So collider physics can help us understand even the nature of dark matter in a way?
In a way, yes. The way people try to do that is to produce dark matter particles inside a collider and study whether we can, whether your hypothesis theory fits into that kind of measurement. Of course, that is a very difficult measurement because dark matter is supposed to not interact very much. So the signal is going to be very weak, and a lot of it is going to go away unmeasured. But it is a very popular theory.
So, just one again simple, curious question: do you consider gravity in your analysis of high energy?
In this field, no, because the interaction that we deal with is strong interaction. This is the strongest interaction of the four basic forces, and gravity is the weakest. So usually, in order to incorporate gravity effects, we have to take into account all those other interactions first, and then we might have some room for gravity. So in this field, usually there is the gravitation effects are so small that it's usually negligible.
As like most of the standard model.
Right.
Yeah. So what is the way forward, like quantizing gravity, or you keep off gravity in corner?
So in most areas of particle physics, we don't think about gravity. Even when people try to incorporate gravitational effects, it's either done classically, or even when try to do it quantum mechanically, it is done at the lowest possible order. Of course, there are candidate theories about what quantum gravity is. But in collider experiments, that is very difficult to do because other interactions are so much stronger than gravity. And if you want to see quantum gravity effects, you either have to make measurements so precise that you would find deviations from classical gravity, or the best way would be to go near a very strong gravity source to study it. So LIGO would be the one that measures gravitational waves very accurately, so that in the hope that we might find something that is not described by classical gravity. We have not seen that yet, but hopefully we'll see something in the future. And a different way would be to study black holes. That is where the gravity effects are so strong that and classical gravity would run into a paradox, because a space shrinks into a point, so that quantum gravity effects would be very important there.
So one last question. What advice would you give to an undergraduate student who wishes to join physics or some related field?
I mean, we'll go high energy physics itself.
I mean, rather I would like to build up on the question. Like, as physics students, we are exposed to multiple disciplines of physics, and all of these are often interconnected also in the modern areas of research. But again, there are different fields there to choose from, and all of them look appealing. And even, I mean, right now we're in our second year, most of us. But let's even in 2 years, it still sounds appealing. How would we go about, let's say, choosing a particular topic of interest that we pursue for the rest of our life? I mean, how did you come to the conclusion that you would want to do this?
Necessary to explore everything.
Well, in my case, I explored either this field of theoretical particle physics and theoretical condensed matter physics. For me, these two choices were very similar in the sense that the tools that are used to study these can be very similar. A lot of condensed matter physics theorists use quantum field theory. Most of our work in particle physics is based on quantum field theory, and of course we use all sorts of different tools to study physics. But in the end, what got me into particle physics is that the physical system that we were studying was more interesting to me. Of course, if multiple fields are appealing to you, then that is great. You could try to choose fields based on the prospects of that field. Of course, that's an easy answer. But what's good about physics is that unless you're going into experiment and focus on equipment, a lot of things, a lot of tools that we use in theoretical physics and also especially in analyses of experimental physics are interchangeable. A lot of the tools, especially if you study numerical methods, those can be used everywhere. So even if you were to choose a specific major in undergraduate or even at master's, there's no reason you have to stick to that field all the way to your PhD. I know very talented physicists who were experimentalists until their masters and then became a very successful theorist at the end of their PhD. So.
And sir, we didn't get your name.
My name is Chung. I'm from Korea University.
Thank you so much.
Thank you, sir. Thank you so
much for your time.
It was a wonderful interaction.
Yes. My face